Dr. Rico here. This is a lecture from my mini course, Robotic Planning and Kinematics. The syllabus and notes are in the description. All right, welcome to Chapter 8, Displacement Matrices and Inverse Kinematics. Things are starting to get fun. First, the introduction. In this chapter, we study rigid body displacements, i.e. motions composing rotations and translations together, composing them. We will represent displacements by introducing displacement matrices. We will discover that displacement matrices have very similar properties to rotation matrices from the previous chapter. So, let's jump right into 8.1, displacements as matrices. Consider two general frames. Fix one frame in space and another with a moving body. Consider also a point P. Assume the two frames are sigma 0 and sigma 1 as depicted in the figure. So we've got a point P, we've got our body, we've got sigma 1 attached to the body, and we've got sigma 0 fixed in space. All right, let's jump in. To represent sigma 1 with respect to sigma 0, note that 1, the origin of sigma 1 with respect to sigma 0 is the origin of 1 with respect to sigma 0, that's our notation for that object, is the vector from origin 0 to origin 1 in the 0 reference frame. Okay. 2, the axes of sigma 1 with respect to sigma 0 are given by the rotation R1 in the 0 frame, as discussed in Chapter 6. So, we've just noted the two important facts about how to describe one of these reference frames in terms of the other. Therefore, the frame, sigma 1, is represented by a pair, the origin matched with the rotation matrix, where sigma 1, 0 is a 3 vector, and R1, 0 is a rotation matrix. All right, changes of reference frame and composition of displacements. Next, let's compute the changes of reference frame. Because the vector from sigma 0 to P, so going back up here, the vector from O0 to P is given here, is the sum of O0, O1, that vector, and this vector, O1P, then we can just express it as this sum, and we can express O1P in the 0 reference frame as O1P in the 1 reference frame rotated with R1, 0. So we obtain the following equation, 8.1, which tells us what P is in the 0 reference frame given the point in the 1 reference frame and the relationship between the origin of reference frame 1 and the origin of reference frame 0. Given 3 frames, frame changes O1 to 0, R1 to 0, and O2 to 1, R2 to 1, what is the frame change O2 to 0, R2 to 0? Let us collect known facts. So we have this fact about how to write point 0 in terms of point P1 and the difference in the origin and the rotation. And we can do the same thing with P1 relative to P2. And we can say that P0 relative to P2 must have that same form as well. It's, of course, a translation and a rotation. In fact, it's actually a rotation first because of the order of operations here. Rotation happens first and then the translation is summed, right? We multiply before we add. That's our standard order of operations. Substitute the second equality into the first. So here's our second equality. We will substitute that into the first by saying, oh, this is what P1 is. Here's our P1. Substitute this entire expression in for P1. We get this expression. We can, of course, distribute R1, 0 here and group them accordingly. So we have our P2 being transformed with this matrix, and we have our origin movement like this. Okay, this implies that R2, 0, so the rotation matrix from 2 to 0, 2 in terms of 0, is R1, 0, R2, 1, And the origin translation is from of 2 with respect to 0 is R10, O21 plus O10. As usual, note the important role of subscript and superscript. So we see that the subscript matches the superscript of the right matrix, right? Or the right point, depending on if it's multiplying a point, a vector, or a matrix. So, matrix representation of displacements and homogeneous representation of points. We're almost there. We can do it in this way, but we'd like to write it as a single matrix instead of a matrix plus another term. To simplify bookkeeping in equation 8.1 and 8.2, we write displacements as displacement matrices and points in homogeneous representation. Okay, homogeneous means that we're using a matrix multiplication to represent not just rotation but also translation, and this is a very common way of doing it. First, instead of using the pair R10, O10, we represent the frame sigma 1 with respect to sigma 0 by the single matrix H10, where we have the rotation matrix as a submatrix here. We have the point O1 with respect to 0, so this is the origin relationship, and a 0 vector and a 1 down there. Okay, so this will be our representation, where O1 by 3 is a 1 by 3 vector of zeros. We call such a matrix a displacement matrix. So it's a displacement in rotation and translation. We can now rewrite equation 8.2 above, so this guy again, as instead of having two expressions where we are we're rotating and then translating, we are now going to write it as a single matrix multiplication, where we say H2 with respect to frame 0 is H1 with respect to 0 times H2 with respect to 1. Again, subscript, superscript matching. That's very intentional, and it helps so much to keep things straight. This result is true because the multiplication between the block matrices works out. So if you do the block matrix multiplication, which actually works just like regular matrix multiplication, where the elements are matrices instead of just scalars. So we do our regular matrix multiplication here with sub matrices included, or block matrices included, and we see that the output, or the product, turns out to have the same representation that we would expect. So the rotation matrix in 2, 0 is this rotation matrix, which we said up in equation 8.2 that should be from our derivation. And we see that our origin in H2, 0 is the origin described here. So it's essentially a bookkeeping thing. It's we constructed these matrices so that this would work out. Okay, you might have noticed this sort of strange way of putting zeros down here and a 1 kind of arbitrarily. It wasn't really arbitrary. We constructed it so that when we do this matrix multiplication, we get back the term that we would like, the terms that we would like in the proper places. So in summary, as for rotation matrices, we note that displacement composition corresponds to matrix products. Second, given a point P, we define the homogeneous representation of the point P with respect to sigma 0 by the capital P super 0 is equal to the regular point P in R3 instead of in R4 with an additional 1 below it, so that we can do transformations of points as well. So with this notion, the changes of reference frame in equation 8.1 is rewritten as the following matrix vector multiplication. So now we see that H10 P1 is equal to P0. So we can not only rotate using multiplication, but now we can rotate and then translate. We summarize similarities and differences in this table 8.1. So here we go. We can represent sigma 1 with respect to sigma 0 with rotations, R10, displacements, H10. So that's the same, right? We can represent a point P, P0, which is in R3, or P0 capital P0, which is technically in R4. It's got that extra coordinate that's just 1, right? How to change reference frames? We simply multiply in rotation, R10, P1. And for displacements, which remember includes rotation and translation, P0 is H10, P1. How to compose displacements? Same again. Multiply with the proper matching subscripts and superscripts. And the inverse is the only place that it's slightly different. We could do the inverse in rotations by just the transpose, whereas in displacements, we can't simply transpose. We have to take the matrix inverse. Okay, so H01 is the inverse of H10. Regarding the last property, the inverse reference frame representation is this. To see that this formula is correct, it suffices to show that this is the case. You get the identity matrix. The inverse, of course, is defined as whatever you multiply the original matrix by returns the identity matrix. So this is something that you can verify, which means that you don't really have to take the entire matrix inverse. You can do this slightly simpler calculation with transposes. Okay, and that's obviously preferred, especially in a big symbolic matrix. The inverse is a little bit messy to calculate. So doing it like this is a lot more efficient and a lot less work. The formula for the inverse frame represented is illustrated in 8.2. So if you want to go from 0 to 1, you transform with this relationship, which we'll call H10, right? And if you want to do the inverse, you transform with what we'll call H01, which is the inverse, and this is the rotation matrix, and this is the origin. So this is represented without the H explicitly there, but of course we prefer that typically. Displacement matrices. The set of displacement matrices, also called the special Euclidean set, is SE. Remember, not SO, the special orthogonal group, or the special orthonormal group. SE, the special Euclidean set, or we'll see it as a group in a moment. H, so the set builder notation. H in our 4x4, which means 4x4 matrices, such that this is true about H. You have a rotation, you have a displacement, you have 0 and a 1, where R is in the special orthonormal group of 3x3 matrices, rotation matrices, and V is a vector in R3. Just like the set of rotation matrices, SO3, the set of displacement matrices, SE3, is closed with respect to matrix multiplication. That is, if you take an H1 and an H2 that are special Euclidean matrices, displacement matrices, and you multiply them together, they will give you a displacement matrix. Moreover, as with the set SO3, the order of multiplication of displacements matters. It's important to note these are not, strictly speaking, the dot product. The matrix product can sometimes be represented as the dot product. However, the dot product is not defined between two matrices, although the inner product in a more general sense is, and it's just our regular matrix multiplication. So this multiplication H1, H2 is the regular matrix multiplication. In general, it's not equal to H2, H1, because we know that's true of matrices in general, and so it's also true of these matrices. And finally, as with the special orthonormal group, the set of displacement matrices SE3 has the properties of a, you guessed it, and I gave it away, group. That is, 1, there's this associativity, okay? So H1 times H2, H3 is equal to H1 times H2 times H3. I4 is the identity displacement. So the identity matrix, 4x4 identity matrix, is the identity displacement. It doesn't take you anywhere. It doesn't translate you anywhere. It doesn't rotate you at all. And for any displacement, H given here, there always exists the inverse displacement, and we've already shown what that inverse is. So those establish that it is in fact a group, and we are happy to continue working with group theory. So that's all we have for 8.1, and I'll see you next time when we talk about the basic and composite displacements that will continue to build our apparatus of displacement matrices. Okay, take care. I'll see you next time.